So they're suggesting the recent increase might just be part of natural cycles or variability rather than a clear human-driven acceleration?
That seems to be the core argument. They emphasize natural variability and also the significant regional variations in sea level change, which, as we know, are substantial.
Mm.
They cite examples like sea level actually falling in places like Stockholm due to post-glacial rebound. That's the land slowly rising after the weight of ancient ice sheets disappeared. While at the same time, sea level is rising much faster than the global average, maybe 3 times faster, in parts of the Western Pacific.
Right.
They discuss the various factors contributing to these regional differences. Thermal expansion, yes, but also the sinking or rising of the seafloor and the land surfaces themselves. It's complex locally.
Okay. And they also mentioned something about low-lying islands.
Yeah, the article suggests that concerns about the imminent drowning of low-lying island nations might be somewhat unwarranted. It cites studies suggesting that some coral reef islands in the Pacific have actually been growing in size, perhaps due to natural processes like the accumulation of coral debris, sedimentation, or even land reclamation efforts. And it makes the point that the Maldives, for example, actually formed during a time when sea levels were higher than they are today.
Hmm. Okay. That's definitely a very different narrative than the one we usually hear focused on vulnerability. They seem to be really focused on separating out global versus local effects.
Yes, they draw a strong distinction between what they call eustatic sea level rise. That's the global change in ocean water volume due to thermal expansion and melting ice, and isostatic changes, which are those local vertical movements of the land itself. They attribute the current global rise, maybe 2 millibar a year historically, increasing towards 3 millibar a year more recently, primarily to thermal expansion kicking in since the start of significant human-caused warming around the 1860s. But crucially, they argue there isn't strong, unambiguous evidence of an acceleration beyond what could potentially be explained by natural variability or measurement issues.
Okay. It's important to hear that perspective, even if it differs significantly from the IPCC consensus. It highlights the complexities and the different ways data can be interpreted.
Absolutely. It's crucial to be aware of these alternative viewpoints and the arguments they raise, even while acknowledging that the overwhelming scientific consensus, as reflected in those IPCC reports, clearly points to an accelerating rate of sea level rise strongly linked to human activity.
Right. Good to keep that context. Now, to provide even broader context, like really broad, the blog post from Chang'an takes us way back in geological time to look at past sea level fluctuations. What can Earth's deep history teach us here?
Yeah, this blog post does a great job of underscoring just how dynamic sea level has been throughout Earth's long history and how closely it's tied to global climate shifts. For instance, way back in the Cambrian period, maybe 500 billion years ago, the Earth was generally much warmer, there were no major ice sheets, and sea levels were significantly higher than today. Or think about the Cretaceous period, the age of the dinosaurs, roughly 100 to 66 million years ago. Global average temperatures were very high then, and sea levels are estimated to have been maybe 100 to 200 meters higher than they are now.
Wow, 100 to 200 meters. That's almost unimaginable. A completely different world map.
Completely different. Then, more recently, geologically speaking, the last 2.5 million years or so have been characterized by these cycles of glacial periods, ice ages, and warmer interglacial periods. During the cold glacial times, massive ice sheets grew, locking up vast amounts of water, and sea levels plummeted sometimes by as much as 120 meters lower than today.
120 meters lower, so huge areas of today's continental shelves would have been dry land.
Exactly. Then during the warmer interglacial periods, like the one we're technically in now, those ice sheets melted back and sea levels rose again, often quite rapidly. Our current interglacial sea level is actually close to the historical high point reached during the last interglacial period, around 120,000 years ago. And it's dramatically higher, about 122 meters higher than the low point during the peak of the last glacial maximum only about 20,000 years ago.
So in the grand scheme of recent ice age cycles, we're currently at a relatively high sea level stand.
Precisely. Since the end of that last ice age, maybe 15,000 years ago, sea levels have risen by that huge 122 meters. They reached something close to modern levels by about 4000 BCE. And that rise wasn't always smooth. It included periods of very rapid acceleration, sometimes called meltwater pulses, when large chunks of ice sheets collapse quickly.
Right. And the blog post also reminds us about local factors, too.
Yes, it also mentions those local geological processes, like isostatic adjustment, the ongoing slow rebound or subsidence of the Earth's crust in response to the removal or addition of ice and water weight, and also tectonic plate movement. Both significantly affect sea levels regionally. And over really long geological timescales, millions of years, changes in the shapes and volume of the ocean basins themselves due to shifts in the Earth's crust also play a role in global average sea level.
It really puts our current situation into such a vast historical perspective, doesn't it? It highlights that sea levels have always been dynamic, always responding to global climate, both natural cycles, and now, clearly, human influence on top of that.
It certainly does. Context is everything sometimes.
Okay, finally, let's turn to that study on snowmelt refreezing up in the Himalayas from the Journal of Glaciology. How does this very specific regional process connect back to the bigger picture we've been discussing?
Well, this study provides a really detailed look at a crucial process happening in a critical region, the Himalayas, often called the Third Pole because of its vast ice reserves. These mountains are the headwaters for many of Asia's major rivers, supplying water to billions. Researchers focused on a specific area, the Langtang catchment in Nepal, and they looked closely at what happens to snow when it melts. They found that a significant portion of the meltwater, about 21% on average each year, in that catchment, doesn't immediately run off. Instead, it refreezes within the existing snowpack.
Ah, okay, so the meltwater trickles down into the snow and turns back into ice.
Exactly. This refreezing process is really important. It affects how quickly water becomes available downstream, and it's also crucial for the overall health, the mass balance of the glaciers in the region. It helps retain mass that would otherwise be lost.
Right, so it's not just melt out, there's melt in and refreeze.
Precisely. The study found the amount of refreezing varies quite a bit depending on elevation and aspect, which direction the slope faces. More refreezing tends to happen early in the melt season. There's also a lot of variation within a single year depending on when and how much snow falls. And interestingly, their computer modeling showed that using hourly data captured this melt-refreeze cycle much better than using daily averages. Those finer timescales matter.
Okay. And what about the impact of temperature changes? How sensitive is this refreezing process to warming?
Highly sensitive. The study found that a relatively modest 2 degrees C increase in air temperature led to a substantial 35% decrease in the amount of refreezing.
35% decrease with just 2 degrees warming. Wow.
Yeah, that has pretty significant implications for future water availability from these regions as temperatures continue to rise globally. Less refreezing means potentially faster runoff, changes in streamflow timing, and faster glacier mass loss over time.
Okay. And did it vary much with altitude?
Generally, refreezing increased with elevation up to a certain point, around 5,900 meters above sea level.
Yeah.
Above that, there just wasn't enough melting happening for significant refreezing to occur. Meltwater availability became the limiting factor. The ratio of refreezing to total melt also showed some interesting patterns with elevation, possibly related to things like the timing of monsoon melt versus pre-monsoon melt, and the insulating effect of deeper snowpacks at higher altitudes. It's complex.
So understanding these detailed regional processes like snowmelt refreezing is really important then. It doesn't just affect local water, but it feeds into our bigger understanding of how the whole cryosphere, all the frozen parts of Earth, is responding to warming, which ultimately connects back to sea level, even if indirectly.
Precisely. While this study is focused on one specific region and process, it really underscores the complex, interconnected ways that rising global temperatures are impacting different parts of the Earth's system. You can't understand the global picture without understanding these regional dynamics.
Okay, let's try and synthesize all of this now. We've taken a pretty deep dive into these diverse sources, haven't we? And it seems undeniably clear that our oceans are undergoing these profound, multifaceted changes. We've got rapid warming, unprecedented in recent geological history, significant shifts in salinity and the layering, the stratification of ocean waters.
Right.
Increasing acidity, which is a huge threat to marine life, and these growing numbers of intense and damaging marine heat waves.
Yeah, the heat waves are really striking.
And then, of course, global sea level. It's rising, and the rate is accelerating, driven mainly by thermal expansion and melting ice. The projections show substantial further rise this century and beyond.
Although, as we discussed, it's important to acknowledge that some perspectives, like the Science Under Attack piece, question the magnitude of that acceleration or its direct, unambiguous link solely to human activity, emphasizing natural variability too.
Exactly. Need to keep that complexity in mind, and understanding those regional processes like the Himalayan refreezing or the calm ice stream behavior is absolutely crucial for building the full picture, isn't it?
It really is. What's fascinating, or maybe daunting, is how interconnected it all is. The heat the ocean absorbs drives its expansion, contributing directly to sea level rise. The melting ice sheets and glaciers add more water volume, further raising sea levels. Changes in ocean stratification can affect nutrient cycles and oxygen levels. Changes in circulation can even influence how quickly those ice sheets melt. It's this complex web of interactions.
Yeah, all pointing towards a planet undergoing really significant, rapid changes.
Hmm.
So for our final thought today, maybe something for you, the listener, to chew on. Considering the vast historical swings in sea level our planet has seen over millions of years, and then contrasting that with the incredibly intricate processes we're seeing now, the ocean physics, the ice dynamics, what are the biggest surprises or the remaining uncertainties that really jump out at you regarding our future climate and our future coastlines?
Yeah, what further questions does this kind of deep dive spark for you? Questions about the long-term impacts, maybe, or the potential adaptation strategies we might need to seriously consider as we navigate this changing world.
It feels clear that while we've learned an immense amount, there's still so much more to understand about the future of our oceans and coastlines, a future that seems undeniably intertwined with the choices we all make today.